So this time we're going to talk about pressure. All right, we've got energy into the atmosphere. We've dealt with temperature, which basically is a proportion to energy. So now we're going to talk about the weight or air pressure. How much is normal air pressure, and why is it significant that we know that in meteorology? So let's take a look at some things here. Let's define air pressure. Air exerts a force on all objects it comes in contact with. Believe it or not, air is putting pressure or force on you as you walk around. And what is that? It's mass. Mass is the number of molecules that are in a certain area. So if you have a whole bunch of molecules, there's a lot of mass. If you have very few molecules, there's not a lot of mass. And then it's times acceleration. Well, acceleration for the atmosphere basically comes down to gravity. So if you have a force, you're going to get mass times acceleration. And air molecules move randomly, so molecules exert a force in every direction on each other. And according to Dalton, the total pressure exerted by all gases in the atmosphere is the sum of each one of those atmospheric gases. So if you have nitrogen, oxygen, carbon dioxide, argon, all of them exert a pressure. Water vapor, when you add them all up, that's the total pressure. So think of it as weight is the force of gravity exerted on a mass. So and the average sea level pressure is about 14.7 pounds per square inch. So every square inch of your body or that building has that much force being exerted on it. That's why if you tried to suck the air out of a tube or whatever, the tube's going to tend to want to crack up, to be pushed together. So structures do not collapse on this because they've got air pressure in them as well. And here's just a barometer to measure air pressure. Mercury barometers used to be the standard. Now they're more aneroid barometers and all that are just as accurate as any mercury barometer. So, and there are adjustments required for gravity variations. When we measure air pressure, we try to be exact as possible. And here's a table of conversion. I like to use millibars. Why? Because it makes the mathematical calculations a whole lot easier with the equations in meteorology. But we're going to talk about millibars and inches of mercury in this course. Another interesting thing, something very different about the atmosphere is it's compressible. So if you put your hand, somehow could squeeze together the air particles in your hand, between your hands, they are compressible. They would gradually get tighter and tighter together, those molecules. However, if you tried to do that with water, water's just going to squirt out. So what does that imply? That means that the atmosphere, the weight of this atmosphere above us, pushing down, is pushing more and more of those molecules closer together, all the way down to the surface so that the molecules are closest together here by the Earth's surface and gradually get further apart as you go up. And because there's less and less weight, the pressure is going to change fairly quickly in the lower part of the atmosphere, but then there's going to be less molecules, less pressure on it, so it's going to change slower the further up you get. That's why the first several thousand feet in the atmosphere is where a lot of pressure change occurs. When you get above that, the pressure is slower, much slower dropping in the vertical. So there's horizontal variations of air pressure. What I want to look at here is a low pressure system went by. See, the pressure dropped and reached about 1,008, maybe 1,007 millibars. The max pressure over here was about 10, 18 millibars. So if you have that, that means the pressure really only changed about 10 millibars over this amount of time. Now, I want you to think about if you walked up a hill. Pressure drops to the fact that in a 150 millibar drop occurs within about 3,000 to 4,000 feet. So not even a mile up, and you've had 150 millibar pressure change. Here we just saw 10 millibars, and we looked at it as a low and a high. And this is a significant pressure difference at the surface and representing lows and highs. So what are some influences that change pressure? Well, rising air temperature. It increases the kinetic activity, as we've learned. And because the atmosphere is not a closed container, what happens? Well, the atmosphere will push the molecules apart. They're hitting each other faster. They're going to bounce further apart. So there's less and less molecules in that area. So there's less mass in that area. So the weight is going to go down if you actually increase temperature in the atmosphere. So if you have very cold air, like in the wintertime, the air is very dense. So if you went in the vertical, the pressure is going to drop very quickly. Now, if you're in very hot weather and you went in the vertical, the pressure will drop much slower. Also, about half the atmosphere, we consider about 1,000 millibars to be roughly the surface of the atmosphere. So if you go to 500 millibars, you're halfway through the atmosphere. And guess what? 500 millibars? That's roughly about 15,000 feet up. Not quite 3 miles. So it doesn't take long to get through half the atmosphere. Also, an interesting thing is the density of water vapor is less than the actual density of air. So the more water vapor, the less dense, the less mass the air has. So it actually weighs less. So if you kept pushing water vapor in, the weight of the air would decrease. I know all of us go outside in the summertime when it's very hot, very humid, and say, boy, this air sure feels heavy. The reality is the air is not that heavy. It's actually lighter than normal. There are other things happening. Winds moving together. If the winds are coming together, we have convergence going on. We're trying to push molecules closer together, and we're going to force the air to move. And if the air is converging at the upper levels, air is going to tend to be forced towards the ground. It's going to hit the ground and then blow apart. If, on the other hand, you have winds moving apart in the upper levels, then the air below it is going to want to rise up, take its place. The air below there is going to begin to converge, so you have convergence at the ground. It's a continuity. So if you have convergence at the surface, you're going to probably have divergence aloft as air is being pushed upwards. And the ideal gas law is basically relating pressure and temperature are proportional at a fixed density. In the atmosphere, density is not fixed. So that picks one problem. And at a fixed temperature, pressure is directly proportional to density. So if the density is changing, the pressure is changing. But if you know 2 out of the 3 variables, you can solve for the third. And think about it, if expansional cooling, the air cools bike tire, releasing air out of a car tire. Feel about the air coming out of that tire. It's expanding, taking up more space. It's doing work, that air. So the temperature is actually dropping in that air. It's cooling. Now, if you're compressing it, you're doing the work. You're providing energy to that air, and therefore it's getting warmer. So if you have a current of air that's rising upwards, an updraft. That air is expanding. It's doing work. It's going to cool. That's why in the troposphere, temperatures cool with height. Now, if you have an interesting thing, say you were out in California, we've all heard maybe about the winds coming off the mountains and making it very hot in LA, for example. It happens to a lesser extent in other areas as well. And we're going to talk about that. But if the air is sinking, it's warming. That's why as the air drops from when it comes over the mountains and into LA, it gets warmer as it's going down the hill. So as it's being pushed down, the air temperature is rising. That's why it gets very, very warm sometimes in Los Angeles when the air is from the east. And here you can see just examples of that. An adiabatic process says no heat is exchanged between the air parcels and the surroundings. So when you send an air parcel up, if it doesn't absorb heat from its area around it, it's an adiabatic process. And most air parcels do that, at least to an extent. So if the air is completely dry, as the air is rising, we can calculate how fast it's going to cool. It cools at 9.8 degrees Celsius for 1,000 meters. So if you went up a mountain, say you went up 1,000-foot mountain, temperature would be about 5.5 degrees cooler when you got up to the top of that mountain. Now, moist adiabat, slightly different. Remember, if condensation is occurring, we learned a little bit about latent heat release. Well, if condensation is occurring, latent heat is being released, so the temperature can't cool as quickly. And this is going to play a very, very important role later as we learn more about meteorology. So with that, just a couple things I wanted to show you this week. Here is the current pressure map. And this is pressure gradient here across the Ohio coming in. It's a pretty significant low. Looks like about 980, 990, something like that up here. And here's your pressure up here coming down with this high is about 1030. So there's a pretty decent pressure across here, but nothing like you see in the vertical. But you can see here, air is convergent into it. Winds are moving in towards the center around the low pressure. So you have convergence here. That means aloft, you probably have divergence. Out of a high pressure, you have divergence in the high. That's why you have clear skies, the air is sinking. And finally, I just wanted to show you the vertical structure. And this is Tallahassee. I could have picked anywhere. The winds change with height, and we're going to talk about that. And we talked about how in the morning, radiational cooling occurs in the lower levels of the atmosphere, the infrared radiation leaving. And here you can see an inversion of temperature. It's cooler near the surface, warmer aloft. But look at this, 1,000 to 900, temperature has dropped, 900 to 800, temperature is continuing to drop. But it almost never drops purely dry adiabatically or moist adiabatically. And there's some clouds up here in the higher atmosphere. And this is just the moisture. The closer they are together, the more clouds. So I just wanted to get you a feel for the pressures, how you can look at them in different perspectives. So I hope you got something out of this. Please let me know if you have any questions.